Okay, lecture 49, balancing redox reactions. Now, this subject seems to confuse students a lot, but it's very procedural. There's only one way of getting these things right, and it works the same way each time. Now, the steps in the book, they include assigning oxidation numbers to start out. And what that is supposed to do is allow us to split this up into half reactions, the oxidation and the reduction. I don't do that because you're going to determine that as you go. What I want to do, we know that one of the species on the left gets reduced, one gets oxidized. When it's reduced, one of them is reduced, I'm not sure which one it is yet, it turns into something on the other side. Well, and then the second species turns into the other thing. There's always going to be 2 and 2. It doesn't have to be. It can get more complicated than that, but that's what we'll have. So if the chromium is the one that is, well, whether it's oxidized or reduced, it has to turn into this one. So our half reaction must be this. Has to be, because this thing turns into something. It can't turn into CO2. It's not going to transmute. It's not going to turn into a new element. And then the other species, the C2O4 2-, breaks up into CO2. Now, I think this might be where the students say, well, how do we know this? I said, well, this is the procedure. We have to break it up into a half reaction. We want to look at each species and what it does. Does it reduce or oxidize? Well, we don't know yet. But we know that the chromium on this side must turn into the chromium species here. Now, we're nowhere near balancing it, so that's the other thing I think that confuses students is where are the oxygens? You know, there's only one chromium here. It looks like it has a different oxidation number. Well, it does. So, but first, just break it up into the two reactions. And then you'll see, once you do a couple of these, you'll really see it. So let's just go through it. First thing we do is we mass balance. We determine we have 2 chromium here, 1 chromium here. And I can almost hear during the my lecture and say, well, what about the oxygens? And so we got to take it step by step. First thing is we balance everything but the oxygen and hydrogen. Well, there's no hydrogen here, and the oxygens we leave till later. So we balance the chromiums. Now, in this aqueous solution, there are only the only thing that's present are these species, and we're saying that we're reacting it in acid, so we have water and we have H+. That's all that we have. And I'm not going to put in the phases here, we're going to assume since they're ions and that we're talking about a solution that they're in water. So we really, in an acidic solution, we have H+ and water to use for balancing. Well, because there's nothing else other than these species. So we have oxygen, there's 7 oxygens, so we balance them with water. 7 waters gives us 7 oxygens, so we balance the oxygens. Now, by doing that, we've added in 14 hydrogens as part of the water. Well, we have the other species that we have is H+. So we put 14H+ on the side. And I think the next thing that gets students is that all these charges, don't worry about those. Just balance the atoms or the ions here first. Make sure you get those all set. So now we have 2 chromium, 2 chromium, 7 oxygen, 7 oxygen, 14 hydrogen, 14 hydrogen. Now, we've done that, so that's the mass balancing. Now we have to balance the charge. The charges have to be the same on both sides. We can't lose or gain charges either. We can't lose or gain mass from one side to the other. We can't lose or gain charge. So we have plus 14 and a minus 2. So the total charge on this side is plus 12. We have 2 times plus 3, so that's plus 6. The other thing that's in the reaction, they're not floating around in the solution, but they're there are electrons. So that's the last thing that we can use to balance. We have plus 6 here, plus 12, so this must be 6 electrons, because electrons are minus 1 each, so that's a 6. So we balanced all of the atoms, all of the mass, we balanced the charge. We have these electrons here, that's new, but that's going to happen during a half reaction. Now, because we've added electrons to this species, this must be the reduction. So by doing the first set of balancing, the balancing of the mass and the charge, we've determined that this is the reduction, so this must be the oxidation below here. Make sure it's on screen here. Yep. So, and we can see that oxygen, we have, that would be a minus 14, so this would be a plus 6 for the chromium, and this is a plus 3, so it was reduced. So you can certainly look at the oxidation numbers beforehand if you want, but by doing the balancing, we're going to determine what was reduced and what was oxidized. So since this was reduced, this had to be oxidized. We have two, so let's do the same thing here. We have 2 carbons, so this must be a 2. We have 4 oxygens on this side. Now we have 4 oxygens here, so we're done with the balancing of the mass of the atoms, the mass balancing. And then now we have a minus 2 here, and we have 2 electrons. Now, if there's electrons on the left side here, then we need electrons on the right side here. Has to be. So if you have electrons on the same side for each half reaction, it won't work, because when we add these back together, the electrons have to cancel, because there's no reaction that we've seen in 1170 or 1050 or previously in this class where electrons were just left out, you know, a real chemical reaction. So half reactions, we get to see the electrons, but when we put them back together, they have to cancel, because when chromium is reduced, it uses up 6 electrons in this case, and then the oxalate ion turns into CO2 and gives up 2 electrons. Well, it has to give up the same number of electrons that were accepted by the chromium. So, but this guy gives up the electrons, it gives it to the chromium, and they have to be equal numbers. So since this is a 6 and this is a 2, and since this reaction, we're free to do anything we want to it as long as we leave it balanced. I mean, as far as the numbers, we can multiply through by 3. So the last step is make sure that the number of electrons transferred is the same. So this is 3 CO. There we go. Now we have the 2 half reactions. Now we add them up. And we have 14 H plus, and you're free to cancel before you do this, because they're well, I guess in this case the only thing that's going to cancel are the electrons, but you can certainly do that. I'm going to just leave them in. I'm just writing them as I see them, so it's not in any particular order, but the left side adds to the left side for both, and then the right sides add up on the right side. And it's going to be a pretty extensive reaction. See if I can fit it all on there. And let me just double check. It's 3, 6, 6, yeah. So the electrons cancel. They should, because as they're being produced, they're being used up, they get transferred, they never go into the solution. So if you had your phases in here, you wouldn't have a phase for, you wouldn't have aqueous for electrons. They never get into the water. They transfer directly from species to species. There's no, sometimes there's waters on both sides, sometimes there's H plus on both sides. Everything's balanced as is. So the final reaction, redox reaction in acidic solution, is this. So as I mentioned that, you know, sometimes there's water that's canceled, sometimes H plus. There's all kinds of things that can happen, and you can get some really large numbers here too. These are, you know, 14 seems large, but they can go way above that. So we got to be careful that we have a lot of play here, a lot of a wide range of possibilities. So just follow the procedure and you should be fine. Now this is the acidic form. The basic one, the way that we do that is we just do the acidic one first, and then we say, well, in basic solution, we wouldn't have H plus, we'd have OH minus. So if that were the case, let's say we had it react all the way through, and then the H plus that's produced would immediately be reacted with OH minus. So we add the same amount of OH minus to both sides. So H plus and OH minus are going to produce waters. So bring this down. So doing the basic solution, and on the exam that's what I'd most likely ask for. I might ask for both, but if I wanted to make sure that you knew all of this stuff, I'd just say balance this in basic solution, because to balance in basic solution means you've also balanced in acidic solution, because you have to do that one first. So now we have 7 waters here, and so we make this 7, and you know, you could carry it down and just make it look nicer, but that is for basic. So that is the way that it would be done. Double check my work here. Looks good. All right, let's try another one. This one a little faster. Okay, so you have to split this up into two reactions, two half reactions. One is the oxidation, one is the reduction. Which one is which? Doesn't matter. I mean, you can certainly figure it out as they say in the book to do. But for me, I know the zinc has to go to the zinc ion. Actually, from here you can see that it was oxidized. This is the oxidation. That's an easy one. And then we have NO3 goes to N2. You might not see how that all works out yet, but we just follow the procedure. Now, since this was the oxidation, this one is the reduction. So, this one was easy to see because we lost electrons, and this one has to be a reduction because the first one was the oxidation. So, let's look at the first one. We have one zinc and one zinc, so the zincs are set. There's no oxygens to balance, no hydrogens, so we just have to balance the charge. So that was an easy one. Now this one, we have two nitrogens here for the nitrogen molecule, one here, so make that a 2. Now we have 6 oxygens, so it's 6 waters to balance, 12 hydrogens, 12H plus, and then we have plus 12 minus 2, and on this side it's 0, 0 and 0, so plus 12 minus 2, so that's a plus 10, so that must be 10 electrons. Now, to balance this, the charges, we'd multiply this through by 5. This becomes 10. And I don't, when it gets to be a really long one like this one or one of the previous ones, I put the number out front. So I'd just say 5 times in brackets and then I'd carry it down. But this was pretty easy. But if you just put the numbers in there, you might get lost. You might forget which one you put you multiplied the 5 by if you get distracted. So just be careful. That's about all that can go wrong here. Now you have it done. And even though this one turned out to be, I chose it because it was an unusual looking one, but it turned out to be easy. Or easier than most, but that's okay. You just follow the rules each time. And of course, if you're in my class and you come across one that is a lot harder than this one, you can always double check with me. I didn't mean to do the 2-1, but there's only a couple that I would say that are in the back of the book, because I've done them all at one time or another, that are really require a lot of effort, a lot more effort than this. Now the one thing that can happen, let's say this had been a 2 here, 2 electrons, and this had been 3. Well, I only had to multiply through by one equation here, multiply through by 5, but if this was a 2 and this were a 3, then I'd have to multiply this equation by 3 and this one by 2, so you'd have to do both to make sure that they'd match up. So that's about as tough as it gets when you are trying to match up the electrons. Now, let's see. Just want to write this out, because this is for acidic solution. To do basic, we do the acidic first, and then what we say is, okay, so we pretended like it was acidic, but now if H plus is produced, it's going to react immediately with OH minus. So we put the 12 OH minus on this side to get rid of all that H plus. We have to do the same thing to the other side to keep it balanced. But these two react together to form 12 waters. And then we have 6 waters and 12 OH minus. Now notice that we have 12 waters here, 6 here, so get rid of 6 here, and this becomes a 6. So they didn't completely balance because they weren't the same number. So if we get rid of 6 waters on this side, we get rid of 6 waters on this side. So we had 12, so we're down to 6, and this would be basic.